Greetings, fellow mathematicians. We're going to take a look at a really good trigonometric substitution problem because it comes down to a tricky trigonometric integral. And it's going to be tricky because it requires two trig identities, which are sometimes forgotten. We'll get to that in a little bit. So let's start by finding the substitution that we'll use. If we take a look at the square root or radical, it's of the form a square root of a number minus x squared. And that's a basic sign substitution. Since the number is 1, we'll be using a as 1. So we'll use our substitution, x equals sine of theta. And calculate your differential, dx, that'll be cosine theta d theta. All right, that's pretty simple. We're going to eliminate the radical using that substitution. So the square root of 1 minus x squared. Make your substitution inside. You'll get 1 minus sine squared of theta. And here we don't have to factor any other numbers out. We can just make use of a Pythagorean identity immediately. We're going to rewrite 1 minus sine squared as cosine squared. And the squares and the square root will cancel out, leaving you with just cosine of theta. And that was also pretty simple. Again, this problem is going to be tricky because it comes down to using two identities. All right, let's go ahead and plug everything in and rewrite our original integral in terms of x as now a trig integral. And what we get, replacing the square root, that becomes cosine of theta. Don't forget to convert dx using your substitution, which we found dx to be cosine of theta d theta. All right, and we can simplify this trig integral as the integral of cosine squared theta d theta. Now at this point, you need to be on top of trig integrals, and here we have sine or just cosine of even powers. And in that case, where you have only even powers of sines and cosines, it's standard to make use of the half angle or reduction identities. And the one that we'll be using is cosine squared theta equals 1/2 times 1 plus cosine of 2 theta. That's the first tricky part for this trig integral. So let's go ahead and plug that in. We'll get this now as the integral of 1/2 and then times 1 plus cosine of 2 theta. If you want, you can bring the factor of 1/2 out, but we can integrate term by term. And make sure you realize we're going to be integrating 1 with respect to theta. Earlier, when you would have integrated a constant with respect to x, the antiderivative would have been that constant times x. But now, we're integrating with respect to theta. So when you integrate a constant, here a 1, that antiderivative will be the constant times now theta. All right, and the other term, cosine of 2 theta, you can use a u substitution or a shortcut that I call the 1 over a shortcut, which I have linked down in the description. So check that out if you're not sure. This antiderivative comes out to 1 over 2 times sine of 2 theta. And at this point, we are done integrating. Our final step, we're going to convert back from theta to x. Now there's two terms here. The theta term, that's a little bit tricky. Now how we're going to convert that, just theta back in terms of x, is using inverse functions. So let's go to our original trig substitution, x equals sine of theta, and let's try to think here, how would we solve this for theta? Or in other words, how do we get theta by itself? Well, cancel the sine function using its inverse, inverse sine. So if we take inverse sine of both sides, we get inverse sine of x equals theta. And that's how we'll convert just theta back in terms of x, which is very standard for trig substitution problems. If you have just theta, convert it back using an inverse function, either inverse sine, inverse tangent, or inverse secant, depending on one of the three trig substitutions that you'll use. All right, so the theta term, we can convert that, no problem here. How do we convert sine of 2 theta, a trig function of theta? Typically, we're going to use a conversion triangle, but make sure you realize this is not just a trig function of theta, but a trig function of 2 theta. You're not going to be able to determine trig functions of 2 theta from your standard conversion triangle. And this is the second tricky part. To use your conversion triangle for trig functions of just theta, we need this double angle identity, sine of 2 theta equals 2 times sine theta times cosine theta. Now let's go ahead and make our conversion triangle and then use that identity. All right, so let's go back to our original substitution. X equals sine of theta. That's already solved for the trig function, but let me flip the sides and put x over a denominator of 1. So I'll write this as sine of theta equals x over 1, and that way we can identify and think of sine of an angle as the opposite over the hypotenuse. All right, and that's going to give us 2 out of the 3 sides for the conversion triangle. All right, and relative to your angle theta, the opposite side will be of length x, and the hypotenuse of length 1. Pythagorean theorem, you can use that here, and you'll get the third side as the square root of 1 minus x squared. And it typically works out to always be the original radical or square root expression from the original integral. All right, now we're going to be using this conversion triangle for sine or cosine of just theta. So to convert sine of 2 theta, let's go ahead and make use of that identity. And we're going to think of it as 2 times sine theta times cosine theta. And now the conversion triangle, we can use it for each of those 2 factors. Technically, we don't need the conversion triangle to convert sine, since you can see right from the beginning, sine of theta just equals x. So we don't need the conversion triangle for sine of theta, but it's consistent. If you really want, sine of theta is going to be opposite over hypotenuse. All right, what we're going to be using the conversion triangle for is to convert cosine of theta back to x. So let's go to our triangle here. And if we think of cosine as the adjacent side over the hypotenuse, we get it. Cosine of theta should be the square root of 1 minus x squared over 1, since we're thinking of cosine of adjacent over hypotenuse. And of course, you don't need that denominator of 1, so here cosine of theta, that's just going to convert to the square root of 1 minus x squared. And there we go. If we just go ahead and write it down, we get sine of 2 theta. We have a factor of 2. We have a factor of x. And then a factor of the square root of 1 minus x squared. And that is it. That's all of the tricky parts for this trig integral. Now let's go ahead and just put it all together. Theta, we're going to convert that to inverse sine of x. So we have theta converting to just inverse sine of x. And sine of 2 theta, we just worked that out. We have a factor of 1/2. And if you go ahead and replace sine of 2 theta with what we just converted to, 2x times that square root, we are basically done. We just need to clean this up. Notice you can cancel out the factor of 2.5 there. And if you want, you can go ahead and distribute that 1/2. And you get your antiderivative as 1/2 times inverse sine of x. And distributing that factor of 1/2, you'll get 1/2 x times the square root of 1 minus x squared plus c. And there we go. This is a fairly standard Calc 2 problem, so make sure you feel comfortable with it. The initial work was rather simple, choosing your substitution, eliminating the radical, and getting a very straightforward trig integral. That's only straightforward if you're on top of all the different cases for trig integrals, what to do here, especially with only even powers of sines and cosines. If you're comfortable with that, using your half angle and reduction identity, and comfortable with this double angle identity for sine, this problem should be straightforward. Unfortunately, sometimes these identities are forgotten, so definitely make sure you know them to be successful in your Calc 2 course. Hope you enjoyed the video. Hope you learned a lot and how we found this antiderivative. If you're enjoying the content, support the channel, like and subscribe.